my pleasure to welcome our next speaker, Mr. Jacob Bamberger, who is a researcher at the University of Oxford in Professor Michael Bronstein's group. He specializes in geometric deep learning with a particular interest in mathematical foundations of the field and is broadly interested in machine learning and structured data. He holds an MSc in computer science from EPFL and an MSc in mathematics from McGill University. With a big round of applause, let's welcome Mr. Jacob Bamberger.
Thank you very much, and thank you for the invitation for me to speak here. I'm very happy to do so. I hope you're having a good time in this really cool program. So today I wanted to talk to you about geometric deep learning. And particularly, I want to show how we can achieve regularity through symmetry. So there's a lot of words, which I hope you'll understand by the end of this talk. So I'll go over several topics, including the curse of dimensionality. I'll introduce the geometric domains, symmetry groups, and see how you can combine all of these to arrive at famous architectures, which are, for example, convolutional neural networks. Let's get started. So all these slides are taken from, or are reordered, adapted from Michael Bronstein's course that he teaches at Oxford. This course is aimed at fourth-year students, senior undergrads or beginning of graduate studies. So it will be more introductory, I think, than the talks that you've seen until now. A bit less research focused, but I think that the principles I'm going to tell you will help you understand the current state of the art of the field. So it's a little bit about me. I guess I got a nice introduction already. I'm generally interested in graph neural networks and geometric deep learning. I guess my CV has already been read, and it's my first time in Nepal, and I'm very happy to be here. I've been discovering Kathmandu, and I really like it. So the outline of the talk is the following. So I'll start with, I think it's important to understanding why we want to apply these fancy geometric tools and these fancy mathematical tools to deep learning. And so I'll start with talking about the challenges of learning in high dimension as kind of a motivation for geometric deep learning. Then I will introduce a bit of the mathematical formalism that is needed to understand the global picture of geometric deep learning. Then I'll go into an example, which are grids and convolutional neural networks as an instance of the geometric deep learning blueprint. And finally, I'll see how we can apply the same geometric deep learning blueprint to other kinds of symmetries and geometric domains, which leads to other famous architectures. So hopefully we'll get like a kind of an idea of how you would think if you want to design like a geometric deep learning architecture, both to the mathematical formalism and to the intuition behind it. So before going into the mathematical motivation, I think it's interesting to think about more of a research motivation in terms of organizing our research. So as you may have noticed throughout this week, there are many architectures in machine learning. Machine learning is a very big field, and it's sometimes hard and overwhelming to figure out what are different concepts. So these architectures, so as Michael would say it, there is a zoo of architectures, right? And so you can see there are GNNs for graphs, CNNs for images, deep sets for sets, transformers for everything, and RNNs. And so geometric deep learning can kind of be motivated by wanting to develop a formalism to be able to talk about all these different architectures in a unified way, right? And so this formalism will help us compare these architectures, but understand why we are interested in developing these and why they are as they are. So that was more of the, cultural motivation. Now is a more mathematical motivation. Maybe Michael has already talked about it, but I think it's nice to review. So in deep learning, we are interested in learning in high dimension, right? So we are often our features are going to be hundreds of dimensions, and we'll have many layers. And so this comes with its problems. And so I'll go into these problems now. So in a very simple way, we can think of supervised machine learning as function approximation. So you have, for example, images with images of cats and dogs, and you want to classify if these are cats or dogs. And basically what you want is to develop a model that will be able to solve this task, right? And often it's called a black box, but as you will see, there are principles that guide kind of the design of these black boxes. So people call this sometimes glorified curve fitting, because at the end of the day, especially in the supervised learning setting, you have your data points and you have labels on them. So for example, here in the red points, you can see some of them are cats, some of them are dogs, and sometimes you have labels on them, so you will say the first 4 are cats and the next 2 are dogs. And so this is what we mean by curve fitting, right? You want to try to draw a curve that goes through all these labeled points, but at the same time, in the blue part where we don't have labels, you also want to be able to generalize, right? You want to be able to generalize to unseen data where we don't have the points. And often, in order to have this good generalization property, you want that the function that you're drawing has some form of regularity, right? I don't know if you've covered this, but there is, right? So maybe you've seen L2 regularization or L1 regularization. This is a way for functions to, have nice properties and be well behaved. And this is against this, the picture of overfitting, where you have a crazy function that goes through all your points, but which is not very smooth, right? And so now we can look into another example. So the example we're going to look at now is the nearest neighbor classifier. So I think you are familiar with this, but the way this works is that, so you have points. Some of them are labeled, some of them are not. And so you want to classify the unlabeled one, right? And the way you're going to do this is that at an unlabeled point, so for example, the labeled point here will be the star point in the center of the picture. So if I'm an unlabeled point, so for example, the top point, the way I'm going to classify this point is by looking around me at my neighbors. I will find the labeled points, and I will look at the labels of my neighbors, and I will compute something with this, and maybe you'll classify it as the majority voting of your neighbors, right? So in the case where you have just one labeled point near you, you'll just classify it as a cat, right? And so the notion of regularity that accompanies this algorithm is that if you want to classify a point well, you want a lot of neighbors that are close to you, right? Because if you have a labeled point that is close to you, it is very likely that your class will be the same as your neighbors. And so in this idealized assumption, we can assume that, so again, we have just one labeled point in the center, and you can assume that our nearest neighbor classifier will classify a point correctly if it has a label at the radius r, at a distance r from this point, right? So in this image, you will get that all the green points are going to be classified correctly because you have a label point that is near it, but the red points won't be classified correctly, right? And the idea here is that, so we can also assume that our data lies in the unit cube, which has volume 1, as you may know. And now you can see that the volume of this ball that I drew, that are all basically the fraction of points that are going to be classified correctly, this has volume 0.78, right? So this was the story in 2 dimensions. Now what happens in 3 dimensions? So now you can see again, you have the green points that are classified correctly, and the red points that are classified incorrectly, right? But now the volume of the ball is 0.5, which is much smaller than before. And the volume of the unit cube is still 1, right? So the fraction of point that you're classifying correctly with this only one labeled point is much smaller. Now what happens when you go, can someone guess what happens when you go in higher dimension? It tends to 0. But what's even more important than that is that, yeah, exactly. Which means that it tends to 0 exponentially fast, right? Which is very, very bad. So if you look at dimension 10, the volume of this ball is 0.002. So if you want to have full accuracy, you you would want to cover this whole cube by these balls. So now you can see if the volume is 0.002, you will need at least 500 balls to cover this cube. But now we're only still at 10 dimensions, right? Not at like the hundreds or thousands of dimensions that are actually used in practice. And so then the volume would be very small. And this is what we call the curse of dimensionality. Okay? So there are many aspects to the curse of dimensionality: approximation, estimation, optimization. Here we only cover the approximation one, which is more like a sample complexity point of view. I won't go into details into the other ones, but I invite you to read about it in Michael's book. I don't know if you've heard about it, the Geometric Deep Learning book. I'll advertise it at the end some more. So the curse of dimensionality that we saw now, it says this: approximating a d-dimensional Lipschitz function with accuracy epsilon requires exponentially many samples in the dimension, right? And now I say Lipschitz function, this is a well-behaved function. You know, you have a bound on the derivative. So even for well-behaved functions, you need exponentially many samples. And so basically, we know that deep learning works on a lot of problems, right? Or on some problems at least. And so we know that these architectures, they kind of mitigate this curse of dimensionality because it manages to generalize. And so what we want are kind of new notions of this regularity. Here it's Lipschitz functions. This we can see as a failure, right? Because it needs exponentially many. Now we're going to try to see how we can develop new forms of regularity. And in many ways, geometric deep learning is a way to encode this some form of geometric regularity to the functions we're learning. Okay? So now we saw the problem. Our solution that we're going to be exploring today comes from symmetries in learning. So yeah, I'll motivate it, and then I'll introduce the mathematical formalism of these symmetries. So for the motivation, so going back to cats, let's say that we have an image data set again, cats and dogs, and we want to classify this. So here you can see two pictures, both are of cats, right? But not only are they both of cats, both are of the same cat, but they're not the same picture. As you can see, one of the pictures is the other one, but shifted a bit, right? And this is what we call a symmetry. And the intuition is that this classification should not depend on the shift, right? A shifted cat is still a cat. And so, yeah, so another example can be seen here. So with letters. So our data set here is, again, two classes, images of letters or just letters. We denote this data set by X, okay? And then we want to learn a label function F, which maps into Y. There are two classes, right? The red class and the green class. And now you can see that, again, the letters that are pictured here, they're all copies of one another, but there is, again, a symmetry. Now the symmetry here is the symmetry of rotation, right? Because if you take an A and you rotate it a bit, it's still an A, right? And so we want this label function to respect these symmetries. If you classify one copy of an A, you want to classify the rotated copy also as an A. Right? We don't want this to happen. Here we have a rotated A that is classified as a B. This is something we'd want to try to avoid, right? So a bit more, here you can see the whole orbit, all of the copies of the A's. Basically what we want is for our function F to be constant on this whole orbit, right? And geometric deep learning, you can think of it as kind of or especially when you talk about symmetries and groups, you can think of it as a way of achieving this kind of regularity. So there are many other symmetries. Unfortunately, I can't cover them here. Here, you can see the symmetry that is more like it's smoother, it's more deformation. If you take an A and you deform it a little bit, normally your function should be stable to that, right? You want that to happen if you want to generalize good, right? Now this is more related to deformation stability, which is another form of robustness, right? But I think the under motivation is the same, right? And I won't go into this, but I think this is a very interesting research area. So here is a bit of mathematics. So again, we can find our label function, which goes from the data set X to our labels Y. And basically, you want the label function function to have this symmetry. And the symmetry can be expressed as, so a symmetry can be thought of as an invertible label-preserving map G from X to X, right? It's the symmetry of your data set. And what you want is that, so if you look at the diagram below, if F classifies, for example, a cat as a cat, then you want the transformed cat to be also classified as a cat, right? And this is what this diagram tries to illustrate. So the goal is to get this invariant, to parameterize these invariant functions in order, so we assume that the task we're solving has this invariance encoded in it, right? And so yeah, we assume that the function is shift invariant. And our goal is to, so one way to do this can be through data augmentation, right? So what we can do is that we start with our training set. And so we start with a picture of the cat, for example, on the left. And we add many, many training points to the training sets, one per shift. And then you train on this. Normally, your function should be able to learn that these are all cats, right? But there are two limitations to this. One is that it is computationally heavy, right? Because your training set now grows very big. And the second point is that you're still not guaranteed that you will be stable under this shift, okay? And whereas what geometric deep learning tries to do is to try to encode this in the architecture itself. This way, what we want is to be able to learn through all these cats, but only by seeing one of them. Okay, so that's one, and this will guarantee us this robustness to the shift. So this is kind of a summary. So we can call this group invariant function classes. Okay, I will introduce what a group is later, but basically you have again this orbit, and you want your function to be constant on this. And the way we're going to do this is to ensure that all our models are already invariant to this. So there's no need to learn this invariance. Okay? And now geometric deep learning asks and tries to answer two questions. How can we leverage invariant function classes in learning? And then a second question, which I think is a bit deeper, is this generally sufficient to break the curse of dimensionality? This is a very hard question, but empirically there has been a lot of successes. So there must be something there, right? And there's also theoretical works working on this, but I won't go into that because that's quite complicated mathematics. The recap. So we introduced this curse of dimensionality, right? And we kind of saw that in order to mitigate this, we can use new form of regularity, right? So if for the nearest neighbor classifier to work, we need this form of regularity. And at the same time, we saw that the target function can have symmetries. If you have your data set, for example, images, the problem, if you have a classification task, the problem often encodes some kind of symmetry. And so what we're going to do next is to try to use these symmetries to model these functions with regularity. For that, we're going to need some mathematics. I hope that you enjoy this as much as I do, because I'm trained as a mathematician and I really like mathematics. So, but okay, if you don't get the mathematical formalism, that's totally okay. There are nice pictures, and I hope you can still get the intuition. Okay. So now we're going into geometric domains. And geometric priors. So if you think of you can see here there's a grid on your left. Often images can be thought of as a signal on a grid, right? So one way you can do this is to flatten the image and feed this image into like a multi-layer perceptron or something. Now having geometric domains kind of doesn't do that because, so as you can see, this vector is very, very high dimensional, right? Now when you look at geometric deep learning, you want to model this more as a signal on top of a domain, okay? And this is what our geometric domain is. It's some kind of structure on which a signal lives, okay? So for images, we have the grid, yeah? And we're going to try to classify signals on the grid. So there are many other geometric domains. Now we've been focusing on the grid and on images, but as you can see, there are many other domains. For example, point clouds, in which you have points, and you have a signal that are on top of the point. So for each point, you're going to have a coordinate or a feature, and you're going to want to classify this. Then you have a graph, which is a bit richer. It not only has points, but but it also has edges. Okay, this is even more structure. However, the structure is not locally. It's not everywhere the same, right? Some points can have like you see it, like the graph is disconnected. For example, the back right leg of the horse, there's like a gap in between. Whereas a mesh will be a bit even more structure, where here you have this local, like every local neighborhood will look pretty much the same because what you're really modeling is a surface. Okay, so these are different examples of domains, and geometric deep learning tries to develop architectures that behave well when processing signals on these domains. So what are signals on these domains from a mathematical perspective? So now we have the domain omega, which, for example, for images, it's the grid. For if you have a textured surface, it's going to be the surface itself. And for a molecular graph, it's going to be the underlying graph, right? But now a signal on this is a map from this domain to something we're going to call C. Okay, most of the time it's just a vector space, right? It's just R to the, so for the images, it's R to the 3. For textured surface, it's also R to the 3. And for a molecular graph, it's R to the m, where m is the number of features, right? So this is the space of signals, okay? This is also a vector space because you can add, there is some structure to this, is what I'm trying to say. You can add two signals together, and there is a notion of linearity. I won't go too much into details in that, but in geometric deep learning, we care very much about these structures. So now that we have, so any questions on, is this clear, the signals? Yeah. So now, when you have a label function, we want to classify these signals on the domains, right? So for example, you can have a molecular task, which is a regression. For example, you want to predict the solubility of a molecule in water. This will be a regression task where the score will be how soluble a molecule is. So there, the y, the target, is going to be R. Otherwise, you can have like an image classification task where y is going to be your number of classes, and it's going to be a discrete valued function, right? And then you can have some a bit more fancy things, such as structured prediction, or like segmentation, right? Now your output, it's not going to be like, it's not going to be collapsed. It's still going to be a signal on the grid, right? As you can see, all you want to do now is to find the contours of the cat. And the output is a signal, okay? So now we can see how many different problems, they actually share a common mathematical formalism. There is the domain, there is the target, y, and in every case, you are modeling signals on top of a domain. And so yeah, so now this is the image that we saw. And now how are we going to encode these symmetries that we talked about at the beginning? How can we use this mathematical formalism to encode the symmetries? And the way we're going to do this is by looking at the symmetries of the domain. Okay, so the domain, so you can see the grid, you can start shifting it already. A grid that is shifted is still a grid. Yeah? And so for this we'll need to understand what a symmetry group is, or at least get an intuition of what it is. So I'll go briefly through what groups are. Okay? Has anyone seen what a group is, or what group theory is? Yeah, I see some nodding. Yeah? Yeah? Great. So group theory is a field in mathematics, which I very much like. I liked it a lot in my bachelor. And it talks about symmetries. Okay? It's a mathematical formalism to formalize symmetries. And there are many applications of group theory in physics, for example, in signal processing. And geometric deep learning tries to use these applications to come up with to adapt them to deep learning, right? So what is a group? So here you have an image of a triangle, and we're going to try to think about the symmetries of the triangle, okay? So if I have a triangle really like this, a symmetry is kind of a transformation of the triangle that leaves it unchanged. Okay, so if you were to blink, and then I move the triangle, and you were to open your eyes, nothing would have changed for you, but I would have seen that the triangle shifted, right? So one such symmetry is the rotation. Okay, if you rotate your triangle by 120 degrees, so if I do this, then it's still the same triangle, right? Can anyone tell me another symmetry of the triangle? Flipping, exactly, reflections. So this is another one. if I do a symmetry, rotating, and then I flip, I can compose them and I get a new symmetry. So this compositionality is very important. And so here you can see I composed 3 rotations. And as you can see, if I rotate the triangle 3 times, I'll end up in the same configuration I started with. Right? You see, does that make sense? Yeah. And now I can also, so I can do the rotations in the other way. Yeah, I can do the rotations in the other way. I can rotate right or left. This will represent the inverse element of the, so if I go left and then I go right, then I will have left my triangle unchanged. Okay? This is what we call the identity element. And yeah, this is important in group theory. Then we have our reflections, which we can also compose. And then you can also add rotations to this. Now, this is the full symmetry group of the triangle. It has exactly 6 elements. And you can really visualize this with this diagram. This diagram is called a Cayley diagram or a Cayley graph. Right? And this gives you, I think this is the nicest way to visualize groups. Yeah, because you can really see what, so if you look at the labeling of the nodes, you can really see how the nodes are, or how the corners are transformed. Okay? There are many other representations of groups. You can have Cayley tables, which are kind of multiplication tables, but for groups, that keeps track of all the information. And okay, now it's a very mathematical slide. I don't expect you to parse this now because it takes a while to digest. But basically, you can see there are 3 main points. The associativity, which talks about the composition of the groups. Then there's the identity element, which is this thing. If you take a triangle and you leave it alone, this is a symmetry. It's a trivial symmetry. You didn't do anything, but it's still a symmetry. And that has to belong to a group. And then there's this inverse, right? If I go right, then I can go left, and it will cancel out. Okay? So very formal, very mathematical. Now we can move on. So now we've seen the geometric domains, and we've also seen symmetry groups, right? So now we are ready to kind of get a better idea of the geometric deep learning blueprint, which is kind of like directing principles if you're looking to design an architecture that will work on geometric domains and their signals. So there are different building blocks. So I'm sure you've heard these words before. There's the linear equivariant layers, which map a signal to a signal, right? And now this equivariance means that if we transform a signal, then the output should be transformed the same way. Okay? We'll go back to this. It's okay if this is not clear. Then there are nonlinearities, which I'm sure you've seen, sigmoid, ReLU, you name it. Then there is local pooling. This is, for example, in imaging, you know, you can do max pooling and you can coarsen your grid. This is also very important. And then there are invariant layers. Invariant layers are usually at the very end of your network. And this is to parameterize these invariant functions that we wanted. Right? You wanted our labeling function to be invariant to these rotations. If I take an A and I rotate it, I still want the prediction to be an A, and this is what we mean by invariant. Okay, a bit more visually, you have basically the GDL blueprint says that architectures can look like this. It's a good way to construct architectures. You stack group in equivariant layers, so linear equivariant layers, then a nonlinearity, then some form of local pooling, and you repeat this, right? And so maybe you recognize this, I think, yeah. So if you look at the bottom is the net. These are the first convolutional networks. And you can really see that this picture at the bottom is very much similar to the geometric deep learning blueprint, right? So the first step is a convolution, then you coarsen, then you convolve, you coarsen, you convolve, etc. Okay? Okay? And you can see that, so any function that is linear can be expressed as this kind of inner product, right? Where V is our space of parameters, there are n parameters. But now we can ask, what are exactly the linear translation invariant functions? And actually, if you work out the map, you will see that there is not a lot of freedom to parameterize invariant functions. So here it says that V should be the constant vector of all ones. This is a bit of a lie. It should actually be the constant vector of one parameter. Okay, so we have one degree of freedom. And what function would this be? this is just summing on the nodes. Okay, summing on the nodes of your grid. And this is, so you can see the space of functions that is invariant and linear is only one-dimensional, right? And this is very powerful because it can drastically reduce the number of parameters that is in our model. Now, a bit more complicated question is, what are the equivariant functions? Okay, so we saw that the invariant functions was kind of just summing. Now, can we do the same game with equivariant functions? Okay, so formally, an equivariant function is so our function f is linear, so it can be parameterized by a matrix that we denote by C. Okay, and by equivariance, we want the C to commute with the shift. Okay, so we want, if I shift and then I apply C, this is the same thing as applying C and then shifting, right? This is what I mean by commuting. And so does anyone have an idea of what such matrices look like? Or what is the operation that is kind of underpinning these matrices? Okay, this is a lot of math and it's hard to process, but we did see one example of such an operation. Does anyone remember what example we saw? The convolution. I heard convolution. And yeah, exactly. So this is exactly what convolutions are. They are exactly the linear equivariant maps. Okay, so the space of invariant functions was just summing. Now the space of equivariant functions are convolutions. And this is what we'll see now. We'll go a bit through the math to kind of understand why. But so what does convolution on a grid look like? Okay, so here it's not only convolution, it's also a local form of convolution where you only care about your direct neighbors. Yeah?
Can you please explain the linear equivalence invariance again?
Invariance? Yeah, of course. So invariance, so typically invariance is going to be at the very end of your network. And this is when, for the whole image, you want just one value. For example, for the image, you want cat. So what you're going to do is that you're going to collapse your whole domain to a point in order to get just one value, right? So basically, it's kind of, yeah, so invariance, and this is invariant because no matter how you, okay, I get why you were confused now. So it's invariant because, so basically the idea is that you want the shift to not have an impact on the label, right? So if I take a cat and I shift it, then it won't have an impact on the label. Now if I take this sum, I collapse everything, now this shift, it doesn't really have an impact, right? It's just on the domain, it doesn't have an impact on the signal. So the sum of the signal, it isn't impacted by this shift, right? And so the label won't be impacted by the shift.
So we convert the data into one single value.
Yeah.
And the single value summarizes the whole data.
Exactly. All the image, right?
Thank you.
No worries. And as I said, this space of function, if you want it to be invariant and linear, is going to be of dimension 1. You will only have one parameter to learn. And this is very nice. So now equivariance, now we get to convolution. And we can think about convolution on a grid. So really, a grid, you can really compare it directly to a graph, right? With this representation, you can think of it as a graph. Now, convolution on this grid will look like the following. So we're looking at the output of the convolution at the red node, and this will be equal to a parameter A times its left neighbor, plus B times itself, plus C times the right neighbor. There are only 3 parameters, right? And this is kind of the recipe to compute the output for any node, okay? So now we have only 3 parameters, right? So convolution is very efficient in that respect. So if we do like we did before, and we represent this signal by stacking them and representing them as vectors, we can see the convolution as multiplication by this circulant matrix. Okay? The circulant matrix is very nice. It has like this very nice pattern where it shares parameters along diagonals. Okay? I encourage you to maybe make I think maybe Federico will talk a bit about this, but I encourage you to make the connection between this and this, right? So just do this matrix multiplication where you have some index I, and you will notice that the output at index I will be exactly that. can represent this, and this is a way to implement this. Now, we have seen that convolution commutes with the shift because it is equivariant, right? You can verify this by just verifying this equation, okay? And what is really fascinating, I think, is that not only do we have convolution implies shift equivariance, but you also have the other way. If you want a shift equivariant map that is also linear, then it's going to have to be a convolution. Okay, you're going to have this weight sharing structure in the matrix. So let's go a bit through the map. So now we're working on the map of this. So on the right we have our filter with the indexing set of the matrix. So on the right is the matrix C, and then at the bottom you have a description of the matrix S. And so what we want to check is that SC is equal to CS, right? And so what we're going to do is to write down what's SC, a description of SC. So S times C at index ij is going to be equal to this complicated term, which is equal to this complicated term. But at the very right, you can see that what pops out is just one parameter. Okay, so you started with n squared parameter, and the value of the product is one of these parameters. Now you can do the same game with CS. Okay, and what you get is you have another parameter, but now you can see that the indices of these parameters are different, right? And so if you think about it, if you compare what parameter this is, you will see, and you try to make these two parameters equal, which is what we want, right? We want this to commute. We want this equality. SC should be equal to CS. And so what we're going to need is that Ci plus 1j is equal to Ci j minus 1. And here I colored the two parameters. And this is where you see that, so now you see that the two parameters that are diagonally neighbors should be equal. Okay, they have to be equal if we want the two matrices to commute. And this is how we're going to reduce the dimensionality of the space of functions we're trying to compute. So now you can repeat this for all values of I and j's, and you will see that all the values on the diagonal should be equal. Now you repeat for every diagonal, and you see this nice pattern. Okay, you see this nice. So all parameters that are of the same color should be equal if you want the equivariance to work, right? And this is exactly what this convolution is in its matrix representation. Here you have the same color encoded, and you can see that the diagonals should all be equal, right? And this is what how you show that shift equivariance implies convolution. Okay. So now going back to maybe things you're more familiar with. So just like seeing the architecture, so seeing CNNs right as they are. But now we're going to see it through the lens of the geometric deep learning blueprint. Okay? So what are the questions we ask? So we ask, what are the domains? What are the symmetries? What are the signals on the domain? And do we want to be invariant to the symmetries, or do we want to be equivariant to them? These are 4 simple questions. And so here are the answers. So the domain is at the very left. It's the plane, right, or the grid. And the symmetry group is called the translation group. This is just the shifts, okay? You can compose 2 shifts, you'll get just shifts. Now, the signals are just images, right? And the shift operator operates on these signals by also shifting them. And now we have figured out, we have worked out the math. Okay, we did the math in 1 dimension, but I promise that it still holds in 2 dimensions, which is the case of images. And so, working out the math, we know that if we want linearity and equivariance to this transformation, we will need a convolution layer. And so this is the one-side summary of convolutions as the geometric deep learning blueprint. So the takeaways are the following. So I hope I gave you some more intuition of how you can, we compared the grids to the graphs, but we also went from, modeling grids to signals on grid and representing them as vectors. And I think this is good intuition to have if you try to implement things, right? To kind of understand the geometric interpretation of the vectors and the tensors. Then we showed that convolution are linear translation equivariance, but we also show the other way. We also show that convolution emerges from translational symmetries. Now, this is a topic I really think is interesting, and there has been a lot of work that generalized this. So a lot of mathematicians have thought about this and have generalized it to other form of symmetries. So even if we saw this one example that you've already seen before, these principles, they kind of go beyond convolutions on grids. They have been adapted to other kinds of symmetries, and I hope that this gives you an insight of how these arguments may work. So the recap of the whole lecture for now is, so we've seen that the curse of dimensionality can be mitigated with new forms of regularity. Then we have developed the mathematical framework which allows us to use symmetries of the domain to define a good notion of similarity, of regularity, right? This regularity comes from this shift equivariance. This is what I mean. So then we showed that the convolutional part of CNNs follow naturally from enforcing this kind of regularity, right? So there is really it's very simple seeing it like this, right? And next we're going to see other instances of the geometric deep learning blueprint and how people have generalized these to other geometric domains. So one application or one other instance of the geometric deep learning blueprint is the spherical CNNs. So here our domain is going to be the sphere, okay? This has numerous applications. For example, in astronomy, you might want to look at the images of the sky, which is, as you know, we live on the Earth and it looks like a sphere. Then the Earth itself is a sphere, right? And you might want to, predict like weather patterns or the wind or currents or anything in Earth science. And then omnidirectional vision. These are like the fancy cameras which film like the 3D, like the cool GoPros that we see today. And so one question I have is, so this is the domain, okay? The domain is the sphere. Can anyone tell me what the symmetries of the sphere is? Rotation? Okay, yeah. See, if you take a sphere and you start rotating it, still a sphere, right? So now we have the domain, the sphere, the symmetries, which are the rotations. This symmetry group is much bigger than what we've seen now. It's so we denote it often by SO3, right? I won't go too much into the details of this, but there is a reference to, so this comes from, so the people that developed this convolution of the sphere are, Taco Cohen and Maxwelling and many other people also. But basically, so we have our sphere, we have a spherical signal, so a signal on the sphere. But now, if we want the learning to be efficient, we want this invariance or this equivariance to these symmetries, right? And so this, we can then apply the geometric deep learning blueprint and go through a lot of complicated math to figure out how to do this, right? And so at the talk you have, I won't go into details in this, we can talk about it later if you want, but these are the mathematical symbols, I guess, that are used to define these things. So you can see that there's an integration on the sphere. You can see that x is a signal and psi is the filter, right? And basically this r minus 1 times u is basically moving around a filter on the sphere. And this is precisely like moving around the filter on convolutions for images, right? And so what you can see at the bottom right is an illustration of the symmetries that exist on a sphere. So there's a rotation, and then it looks like a translation, but if you think about it, the translation is like a rotation on another axis. So that was I won't go too much into details here, but then you can also have signals on the group itself, and this is how this is how you get this equivariance. So I think this is a cool example of how, so we know CNNs work well on images, and we know that there are other geometric domains which have potential applications. So we're going to try to adapt what works on images to these other geometric domains. A nice domain is the sphere because it has so many symmetries, and then probably you will need less parameters to learn nice architectures on this. Okay. So another example is deep sets. So deep sets is an architecture that processes signals on sets. I don't know if you've been over deep sets or if you're familiar with it. No? Good. case of graphs, okay? So it's graphs without edges. Okay, so you only have your nodes, you have no edges. Yeah? Then every node U has a feature, right? So we have a signal on our set. And importantly, the elements are unordered, right? A set, there is no order in a set. So this is a simple object. It's the simplest in our zoo of objects. And most of what you do with sets, there is an analogy to do with graphs, because a set is a specific instance of a graph. So whatever you do with a set, you can try to generalize it to the case of graphs, right? And it's important in many applications. For example, if you have a point cloud in computer graphics and in vision, you might want to use this kind of architecture, because this is designed for, right, a point cloud is just a set with features, where the features can be the coordinates or maybe some other kind of feature. So can anyone tell me what the symmetries of a set is? Anyone has an idea? Permutation, exactly. So because I want to be able to process signals on this, and I want to use like a machine learning, the standard machine learning tools and libraries, I'm going to want to put the signal on this in a vector format, right? Or in a tensor format. And then this puts an ordering on the nodes, right? Because you're going to have to put one node at index 0, another node at index 1. And this is where the permutation comes into play, because I've picked an order, and now I want my architecture, if I want to classify this point cloud, I want it to be invariant to the order, right? Or equivalently, I want it to be invariant to the permutation. Now, if my output should also be a signal on this point cloud, I want it to be equivariant to the permutation, right? And so now we can, so this is the slide on permutation invariant functions. So if you want so we want permutation invariant functions, for example. So this can also, as I said, this generalizes to graphs. If you want to classify a graph, you're going to want, again, if you have a graph, your nodes, and you want to model a signal on the graph, which are just like the domain are the nodes, right? You want to stack them into a vector. Again, you'll have this thing with the ordering. And this is where the permutation group is also important, why the permutation group is also important for graphs. So let's talk about invariant functions. So as you can see, I've modeled X, I've stacked all my nodes, all my features into this vector X, which belongs to our data set. This is a subset of d-dimensional space. There's a typo there. But basically for each node, you have a d-dimensional feature. And we want to learn classification of a point cloud, for example. So we'll have a label function from X to Y, right? And we want this function to be invariant to permutations. So, so basically there are mathematical formulas that, how you would write permutation equivariance. And now we can ask, what are the permutation invariant functions, right? What are they? So there are theorems, there are mathematicians and computer scientists that have thought about these. And in fact, you can find nice parameterizations for these invariant functions. So you can see that an invariant function can always be decomposed as the composition of, so you first apply psi to every node in your set. Then you take the sum. This is how you get invariance. And then you apply another function, phi, to this output, right? And this theorem says that any permutation invariant function, so linear, nonlinear, anything, can always be expressed like this. And this is kind of a motivation for why you would want, this is kind of a motivation for these architectures, right? So the first part with the psi is going to be equivariant, because you remain at the node level. Then you take the sum, so you've collapsed everything. And the last part is invariant, okay? So the sum can be replaced by other aggregators. And the what? The last one. Okay, so this is So let me think about this. Exactly. So I think that's a good way to think about it. So if you take the sum, then you have an invariant function, but you might still be restricted. Now you might need another MLP or something which is expressive to be able to move around the values, right? Yeah. summary of deep sets as the geometry deep learning blueprint. So you have our domain, which is our point cloud. We have a permutation group. Now, the equivalent of the shift operator that we saw before is the permutation matrix that will act on the signals and permute them around. And then you will have a permutation invariant function if you want to do invariant classification. One such architecture, or a very similar architecture, it's not deep sets, this is PointNet, I think, where they have many applications where they do point cloud segmentation. So for example, at the bottom you want to, for example, classify objects, and then on the right you want to like segment your image. So you can see the airplane is segmented into the central part and the wings and the tail. And these are the kinds of architecture that you're going to use. So this looks very complicated, but if you look at the top, you can see that the first part, they are all n by something. And so they keep information at the node level, right? They are equivariant. And then at the end, you collapse everything to get a global feature. And this will be invariant. Yeah? And then you get the output, and you can do whatever you want with it. And to get the segmentation, this is an equivariant task, right? Because this is, the segmentation is an output at the node level. So the takeaway on deep sets is, so sets are the basic object with permutation symmetry, right? Permutation, invariant, and equivariant functions on sets have simple forms, as we saw with the theorem. And deep set can kind of be thought as a universal blueprint for learning on sets. Okay, there will be many different architectures, many different tricks, etc. But supposedly it's a good idea to do this equivariant and then invariant layer. So I talked about reducing the number of parameters, and this is kind of a slide that resumes this. So at the beginning, you know, if you want to parameterize any linear map, so all kinds of linear map, you will have n squared parameters, right? You will have, each pixel will have a parameter on its own. And this corresponds to when the symmetries are trivial. You don't have a restriction on like a equivariance or invariance restriction on the space of functions. Now next, we saw that you have the translation part, where, so when you want to satisfy translation invariance or equivariance, you're going to get this weight sharing on the diagonals, right? And now you've reduced the number of degrees of freedom from n squared to n, right? So this is a big reduction, right? Okay, it's like both are polynomial, but one is linear, right? And then if you want to go further and you want permutation invariance or equivariance, you're going to restrict it even more. So then here you're going to have 2 degrees of freedom, right? So we saw like a very general statement of this theorem. This is for linear maps, right? So basically the idea here is that you have one parameter on the diagonal for the impact a point will have on itself, and one parameter off diagonal for the impact other nodes will have on you. But each node can't do the difference of other nodes, right? And this last point, so this is only 2 degrees of freedom. This is nothing, right? And this can be thought as, so this is also the case for graph neural networks. Often you're going to have just 2 degrees of freedom, right? I don't know if probably you will see this a bit more with Federico, where you have very few degrees of freedom because you don't have enough structure on the graph to have this, to have like nicer symmetries. And this can be a source of lack of expressiveness of graph neural networks. If you've heard this, these are like topics of research that are currently ongoing. I won't go more in details with that, but too few parameters can sometimes be a problem if the symmetries are too strict. So this is kind of a recap, on grids versus graph. As we saw, the grid is a graph, but it has more structure. There is this local structure. So at every node, you know you'll have yourself and you'll have 2 neighbors, right? Whereas in a graph, you will have neighbors, but the number of neighbors might differ from node to another. So you can't really apply this parameter sharing that is nice, right? There is no nice way to do this nice parameter sharing. So permutation for graphs and translation for grids. And as we saw, you have 2 kind of, for graphs where you have the permutation group, you have 2 kinds of parameters, the red ones, which are for yourself, and the green ones, which are for your neighbors. Whereas the grid, you'll have a right neighbor and a left neighbor. And if you were to look at non-local convolution, maybe with a bigger receptive field, you'll have more parameters. But now you can think about like further and further neighbors, right? So again, the matricial representation, if you were to take your signal on your graph and you stack them as a vector, then the matrix you would use to do graph convolution looks like the one on the left. Whereas the matrix you would use to do the grid convolution looks like the matrix on your right. On the left you have only 2 parameters, on the right you have 3. But again, this can be extended further. So then is a topic that I think is very cool, and this is an example. So it's a roto translation equivariant GNNs. This is so we'll go into what this means, but this is an example of you have different symmetry groups and you're trying to combine them. And I want to convince you that it is possible to do so. Again, I went faster than what I thought, so I thought I would be rushing through the slides, so I didn't put too much details. But so the symmetry group that we're interested in, so this is a GNN. Again, we're processing graphs, so there will be the permutation side of things. But at the same time, we want it to be, we want to include rotation and translation symmetries. So you can think of this. So the use case is this. You have, like, for example, particles moving around in space, right? They each have coordinates, okay? So the features of each node will include coordinates. But if you have a set of systems, like a system with many particles moving around, if you take the system and you rotate it, it should be the same, right? So it should be invariant or equivariant to this, right? The dynamics, if I'm here, should be the same as the dynamics if I'm here, right? And so this is what we mean by it should be roto translation equivariant or invariant. And what this paper does, they do just this. So they use the benefits of graph neural networks, this locality and this good inductive bias, to try to model these dynamical systems, which come in many problems in the sciences. And so, yeah, so you can see on the right, there's a diagram illustrating this equivariance. So you have the equivariance, this is the equivariance of rotation. So you can see the features at each node will correspond to, so you have features in blue, but you have the coordinates in red, which look like an arrow. And this is coordinates, right? It's a vector, it can be thought of as a vector. And now you can see that, so going from left to right, you're rotating the whole graph, right? You've rotated it, and the arrows also rotated with it. But the network that you want to parameterize, this phi, you want it you want the output of phi to also rotate, right? So yeah, this is like evolving. So you can think of this as an evolving dynamical system. Phi represents a unit step in this dynamical system evolving, right? Okay, so I only had one slide on this, and originally, I think we might still share it with you, but we have a tutorial on it trying to implement this, and trying to check for the symmetries this network respects. So this we realized was maybe a bit hard. So the actual tutorial will be first on graph neural networks, which we think is a very useful thing to get familiar with. And then we'll also share this tutorial about this, and this can be a bonus, okay? So now I'm coming to the conclusion, right? So we've already managed to unify kind of these 3 architectures already. And basically, I hope I've convinced you that with geometric deep learning, we can kind of think about all these architectures in a unified way, okay? There are many things I haven't talked about, of course. I focus on symmetries, but as I said, there are many other ways you can have this nice notion of regularity. For example, this deformation I talked about. And again, so these are not necessarily, these will more be specific instances of these architectures, but I hope I convinced you that thinking about these geometric problems can give you an intuition of what architectures will work when. So here you have a table where you have different architectures on the left, the domain, and the symmetry group. So really seeing all of these architectures as the geometric deep learning blueprint. So we've been through CNN, spherical CNNs. We've been a bit through GNNs, and we've seen deep sets. Now I think you had a lecture on transformers. I think think intrinsic and mesh CNNs are interesting. Um, I recommend you reading about them. They're very geometric. And then LSTMs, I think, is a bit of another beast, but again, the domain, as you can see, is a one-dimensional grid. And you have the associated symmetry group. So, yeah, this is all I prepared for you today. And I recommend you, as I promised, never mind. I was going to advertise the book, but if you're interested in wanting to read more, feel free to come up to me and ask me about more articles. And I really recommend the book. I think it's a good resource to get introduced to this. And it comes with YouTube lectures that are available online for free. And I also recommend this too. And thank you for listening again. And I'll take any questions.
Do you have any questions?
Yeah, I think there's one with the microphone.
Thank you. So, as we discussed that permutation has symmetry of sets, so that means if we change the order of the members within a linear order, it will remain the same, right?
Yeah.
So, is it only from symmetrical point of view or functional point of view as well?
Right. So the way I understand your question is this. So we have the domain, and this is right. The domain is the set, and we have the symmetry of the set. And now we also have a signal on there, right? And basically, I didn't go much into details of this because this needs more mathematics. But once you have a symmetry of the domain, then you can naturally lift this to a symmetry on the signal. So if you have, right, a signal, and you have a symmetry of the domain, then you get the same symmetry on the signal. And so I think also on the signal. Was that your question? Or?
Exactly. So, but it won't affect the functionality of the system, right?
No, in fact, yeah, it won't affect the functionality of the system. But for example, if you have like a point cloud with a center point and a circle around the center point with signals on this, then it's important that the signal remain attached to the same point, right? So if you permute the point, then the signal should also permute with it. Does that make sense? So you need to keep like this attachment of the signal to the domain. But the functionality, yeah, it doesn't change.
Thank you.
Yeah. Do you want the mic so other people can hear you? He's here in the second.
When talking about invariant, I think you told about the summation, but I think the multiplication also does the same job. Is it also equivalent or what? I just want to.
Yeah. So so you have many inputs, and you're taking the multiplication of all the inputs.
Yes.
Yeah, this is permutation invariant, right? Because if you multiply a product, like A times B is the same thing as B times A, right? So that's a really good question. The first thing is that this map you're describing is not linear, right? Because if you take x, what do you think about this? Yeah, right? If you take a vector like x1, x2, x3, and y1, y2, y3, you can do the map on x1, x2, x3, which will be the product of these and the product of that. But now you want to if you addition the two, so x1 plus y1, y1 plus y2, y3 plus y plus x3, and you take the product of that, this is not equal to taking the product. Sum of products is different than product of sum, right? This is basically what I'm saying. So what we showed here was that the linear equivariant ones, they become addition. But there are non-linear invariant ones, like you just described, right? But basically the hope with neural networks is that you have this universal approximation property. But basically by stacking many linear ones with non-linearities, I will...
Is there any other question?
Thank you again.
Thanks so much, Mr. Jacob Bamberger. I would just like to request Ms. Kasuma from NAMA to just come over and hand